length. That is the natural feature we are interested into right now. So, for each node, we can just define the average geodesic distance. So we take each node of the network, and we see how far it is, that very node, from every other node in the network. Why it is interesting? Because it gives you an idea of how well connected, how central that node is. It's just a symbol of the many centrality metrics there are, and the most famous centrality metric is Google PageRank. So that is a very, very simple thing, but anyway. And we can just make the average, and then we make the average of the average, and that is the average shortest path length. That is just a number which gives you an idea of how many hops you have to do when you start from a node and you reach another node. So on a network with a very low number here, it means that basically everybody knows everybody, okay? Or at least knows somebody that knows that person. And if you think about, for example, a power grid, it means that there are not very hops between the power plant and the consumers, okay? And the Curtis path length is just the median of the averages. And we will be using that more than this because it's very more, well, it's faster to compute, basically. Here, we are into this property because I like the algebraic side of things. And basically, I found this extremely interesting because usually on computer science textbooks about graphs, the matrix point of view is overlooked, basically. So, if you just take the adjacency matrix of graph and you make its kth power, so you multiply the matrix k times, for example, then you have a matrix that in position aj has just the number of paths that start from I and go to j, which have length k. And so we have this example, this graph here, and for example, from 4 to 8, you can go with 2 paths of length 2. That is, for example, I think here, this one, okay? That is 2. And this kind of computation is very interesting because matrices is something that scientists are very good to optimize, parallelize, all that stuff, while regular graph algorithms are often very hard to make parallel, okay, unless you do something like MapReduce. So it's just a different point of view. And what is on the diagonal, on the main diagonal of the matrix? If you have just the adjacency matrix, we know that here we have all zeros because every node is not connected with self. But here, what it is, if you take a node, that is the number of paths that start from that node and arrive back to that very node. So it means that it's a number of times you can just jump to a neighbor and jump back. So that is just the degree of the node. Of course, it's a very bad way to compute that that quantity because, well, multiplying matrices is rather expensive. But still, it gives you, that is the meaning of the diagonal of the square of the adjacency matrix. And we have finished with the shortest path length and that related matrix like the diameter, which is the maximum shortest path length of any 2 nodes, okay? And we start with this one, the clustering coefficient. Start by defining the local clustering coefficient, which is a metric for each node, okay? And we count the number of triangles that have that node as a vertex. So in this example, X is a vertex of 3 distinct triangles. That is this one, and this one, okay? And then we divide it by the total number of edges that the friends of the node can have. So we have removed the X node, we have just the friends, and we see that that is the maximum number of edges that are there if the graph were a complete network, okay? And so it's this number is just the binomial coefficient with the degree here and 2 below. And these are the only edges that are edges of the triangles. So eventually we can just count them and divide them by the total number of, which is these dotted edges, okay? And we get this number. Basically, well, then we just make the average, that is a network-wide feature, which is a measure of transitivity. Basically it tells how often it occurs that two of your friends are friends themselves, or if you prefer, how much it occurs that two devices connected to a third device are connected themselves. Two websites connected to the very same website are connected themselves, that kind of stuff. And somewhat it gives you a measure of how resilient is a network, because if you have a very high number of triangles, for example, if you remove that edge here, well, when you the paths, the shortest paths that went through this edge increase just by a factor of 1, because they have to do this or this, okay? So the network stays connected. So if you have a large number of triangles, the network is rather robust, okay? And we conclude with our familiar matrix notation here. How we can just count the triangles. Well, what is a triangle? Isn't it perhaps a path that starts from a node, arrives to that very node, and has length 3? Yes, it is. So we can basically just take the third power of the adjacency matrix of the that is the main diagonal. And so here we use the average clustering function of network X, which computes the average clustering of the graph, that is the clustering coefficient. They call it average clustering, but anyway, that is. And here we write that function using NumPy. We make here the third power of the adjacency matrix, take the diagonal. Then we sum on the rows or on the columns of the adjacency matrix in order to get the degrees. We just take these in order to exclude the nodes which have just one thread, okay, because they are not relevant. If you have just one friend, you can be part of a triangle because you have to have at least 2 edges, okay? And then we just make some averages and some divisions here to have the number, okay? That is pretty efficient, apart from this, which may be quite expensive.
Did you happen to compare the execution time of the two implementations?
Well, it depends, because this is not very efficient as well. I mean, on small networks, they are both very fast. And on very large networks, if you just take a network X graph, it's going to fill your whole RAM, and so it's not going to work because of that. We have a slide that compares that too. So basically, I believe that there is not a huge difference on average cases. And these can go pretty up. But anyway, we have a section that is about approximations. Because if you have a very large network, you just can't hope to use these regular algorithms. We will be seeing that in a bit. And that is the third network feature. Okay, we have every node-wise property. We can study its distribution. Okay, we have many nodes, and we can study as a whole. But sometimes that doesn't convey far more information than just the average. So, for example, we we usually do not study the whole the whole shortest path length distribution. On the other hand, the average degree is not very informative on the network, so we study just the whole distribution. And people have been believing that networks have a power law degree distribution. So that is the degree distribution, just count the number of nodes with a given degree and divide it by the number of nodes. So people have been believing that these kind of networks, citation networks, biological networks, the 3W graph, internet graph, and social networks have power law degree distribution, which tends to be a linear a linear plot on the log-log, on a log-log plot, okay? And that is the shape of a general power law distribution. That is, it is proportional to the decayed power of minus gamma here. Gamma is a coefficient that is greater than 1. And for real-world network, it's believed to be around 2, 3, 4, something like that. Usually we do not have larger coefficients. And so this is an example I made just generating the data with statistic functions. So it's not that clean. That was just to give you an idea. That is more like real data. You have a bit of a spread here, okay? And the idea of the power law, that is also called zip flow, Pareto law, depending on the field from which it comes the definition, is also called the 80-20 law, because basically it means that 80% of the nodes, for example, account for just 20% of the edges. That is the idea. That kind of law was discovered also in economics, and it's believed that 80% of the people own just 20% of the riches, or the other way around, just 20% of the people own basically everything. In our case, it means that few nodes account for the vast majority of links, okay? And also that most nodes have very few links. If we reason on that, what it means is that it gives you the idea we have a core with a very connected networks, high degree nodes in the core, and then a fringe of nodes that are attached around the core with few connections, okay? And if you are into maths, there is also a very nice proof that a power law implies a super short diameter, okay? But anyway, nowadays, this is the idea, okay? So that the core, the highly connected core, with some nodes that just go out from the core with just one connection, and some isolated communities and people with no connection. Well, this is typical of online social networks when, for example, this guy signed up but never made friend with anybody and didn't use the system probably. In a human social network, real world and human social network, this is very unlikely because it means that someone was born and nobody took care of him. We usually just ignore this kind of things because there is no meaning in that. They do not participate in the network. So the only information which is interesting if there is a very large number of them. Okay. So for example, if you're running a site, a website with social stuff, if you have a very large number of eyes, it means that a lot of people just logs in but doesn't care of your system anymore. But anyway. What we want to do is find the connected components, and especially find the largest connected component, which is the one we are interested in, the core, okay? It's the one which we usually study. So the assumption we made about a connected networks now makes sense, because we are just taking the core. We'll be seeing that the core usually accounts for like 90% of the network, so it's very relevant item. We can just study that and derive interesting conclusions. Here we're using the same, well, it's very small, the font, sorry, that is copy and paste from EuroPython netbooks, and I hoped it would be a bit better. But anyway, this is the network X connected components function, which returns a list of lists, and it is a function that is in the sparse submodule of SciPy, okay? So you can just give it a matrix, and it gives you an array, which in each position tells you that node, the node with that index, in which connected component it is. And we apply that function to that graph, but anyway. Also for math people, if the matrix, the adjacency matrix is primitive, then the network is connected, but anyway. This kind of consideration is very relevant if you want to compute the Google PageRank, for example. Basically, lots of computation that are done are made in order to make sure that the graph is primitive. So because the starting graph of the web links typically it's not. You can have nodes that are not connected with everyone else, and so it's interesting. Last year I had some slides on that, but this year I decided to change a bit the subject, so it has been excluded. This comes from a Facebook app, maybe you have used, and in this case you are a dot here. So that is the Hugs application. Basically you could send hugs to people on Facebook. I am not on Facebook, so I've not used that, but anyway. And this is typical degree distribution of a real-world social network. So we have to ignore the small values, because for low degree nodes, they do not follow upper low usually. Okay, we just completely ignore them. We try to find from which degree the power law starts. Okay, and then also for very high degree nodes, we have fluctuation statistics. So it really doesn't matter if they are so scattered, because you have to consider that a power law predicts that there are high degree nodes with a very higher probability that you would have, for example, with an inverse exponential distribution. So it is a very, very strange distribution. Okay, you have you have outliers with high probability. Okay. Besides, most people nowadays believe that what we have found to be power laws are not power laws, but other fat-tail distributions. So what we know is that social networks, complex graphs, have a fat tail. That is to say, they have lots of high-degree nodes, many more than we would expect from, for example, an exponential distribution, a Gaussian distribution, that kind of stuff. Okay, that is true. Then, if it's actually power law, well, we are doubting that, because many researchers just plot things on a log-log plot and then take a ruler, and if it's a straight line or less, then it's a power law, which of course does not work. In this table, I gathered some data from papers of people who sampled online social networks, and we can learn a lot of things here. Well, first, this one in green above are complete network samples. That is to say, the guys running Cyword gave the researchers the whole data set. Cyword is a very popular social network in Korea, I think. Okay, and so that is full. That is not a sample. It's every single data, well, anonymized, of course. This one, for example, is just a random sample. It's red because it's under 1% of the number of nodes, so it's not reliable at all. They stand in between, and for these I didn't find clear information on the size of the sample. So we have to be careful on the kind of conclusion we draw from this kind of data, because, for example, these two studies regarding Twitter, this guy says that the average degree of the nodes is a bit above 20, and this guy says it's a bit above 400. So I don't believe this can be the same network. It's just missampling. They make statistical error, probably, they made. Okay? What we can really be sure of is that the CPL is short. You see that you may have some million of nodes, but the CPL is just in the order of 2, 3, 4, 6, something like that. We say that social network, complex network, have a short diameter, shortest path length, average shortest path length, in the sense that it's basically logarithmic or under logarithmic in the order of the network. Okay? So, oh, sorry. This is to be expected, and we found that in real networks. The other thing that we can find is that the clustering coefficient C is in the order of 0.2, 0.3, which means high. Okay? We remember the clustering coefficient for the way which is defined is a number that goes from 0 to 1. Okay? And we say that 0.2, 0.3 is high, because if we took a random graph, which we'll be studying in the next slide, then that number would be like 3, 4, 5 orders of magnitude smaller. So that is high. Okay? Only very regular lattices have a higher clustering coefficient. Complete graphs have 1, for example. Okay? But it's not like networks are made, real-world networks, I mean. And this is the model to create random graphs invented by Erdős, okay, and Reni. The idea is that you have a huge urn with all the graphs inside, and you just draw a graph. In fact, you are independently drawing all the edges. Each edge can be there with a probability p. Okay? So the edges are independent, one from the other. These are some metrics which are have that values with very high probability. So if you just draw a graph from this process, then with very high probability it has the features I mentioned here. There is a bit of confusion between a random graph, which should be the process to create random graphs, so really an ensemble of graphs, and a random graph as one graph drawn from that urn. Okay? So we can just say that a graph is random if it looks like a graph, one of the graphs that come from the random graph urn with very high probability. That's the idea. And that is not a very good model for online social networks, because the clustering coefficient is p. And what it means? Well, every edge is independent. So what is the probability that two of your friends are friends themselves? Well, that's p. Because everything is independent. Okay? And the diameter is logarithmic. Well, under logarithmic, in fact. And the degree distribution is not has not a fat tail. That is an inverse exponential, basically. No, sorry, Poisson distribution. But we have to be careful. When we say that is not a good model for social networks, what do we mean? Well, there is a single issue of a real-world social network, real world, that has this degree distribution. Some researchers went to a high school, and they made interviews to the students about their romances. So they asked everybody, who did you go out with, and that kind of stuff. Then they studied the resulting graph of the connections. It has been found to resemble a random graph. So you can decide two things. If you don't care about statistics and you are into suggestive interpretations, then you can say that if you weren't very successfully in high school, then it's not your fault because it's whole random. In fact, it's not that way. We can just think that it's not a very transitive relationship. Well, if one person goes out with two different persons, that two different persons are not very likely to go out themselves together. Okay? This is not Franchi graph. We could also say that basically we expect it to be bipartite. So basically all the males have vast majority of links toward the female set and vice versa. So it's a bit different. So we have to be careful to define what we mean with real-world social networks, because really they can be very different. Okay? This is another model they created to explain the short characteristic path length and the high clustering coefficient. Okay? It's very nice. They just start from a circle of nodes. We connect each node with the neighbors, okay? And then we rewire each edge with some probability. So we introduce these long-range links, which are attached to faraway nodes with just random probability. This gives us a high clustering coefficient and a short diameter, okay? Short characteristic path length. That's interesting. This is basically for a wide range of P, it holds. And eventually, we arrived to this, the Barabasi-Hilbert model, which was created to explain power laws in the degree distribution. That was when people believed that really graphs had a power law degree distribution. Okay, so the model is like this. You start with n0 nodes, and at each step you introduce a new node that is connected with m existing nodes that are chosen according to preferential attachment. Preferential attachment means that rich get richer. So if you get a lot of connections, you are more likely to receive these new edges than you would be if you had no connections. Okay? And when you have this kind of process, then you have a power law, or at least a fat tail, that has been proved. If you take the same model and you just choose the nodes with an uniform distribution, then you get an exponential degree distribution. So if you want to create this kind of distribution, fat tails, you have to put some preferential attachment in that. In fact, real-world networks, like the internet graph, do not follow this model. It has been proved that there is some randomness. So very low degree web size are slightly more likely to receive links than a pure power law model would predict. But anyway. And now we start the part about efficiency, because up to now it was an awful lot of maths, but we are into computers, into Python, and we want to run things. So I gave you some ideas, but if you want to study large networks, they're not going to work. NetworkX is not going to help you because the computational time is going to blow up, and the memory as well. So, for example, this is Dijkstra's algorithm that has been widely studied in computer science degrees. Okay, and I briefly review the algorithm here. We have a dictionary which holds distances of each node with the source, which is a single node. This is a single source, shortest path length. So you are taking one node and seeing how far are all the other nodes. Okay, and this is the predecessor dictionary. In scene, we put the nodes we have seen with the distance from the source node. So we start with source, which is at distance 0 from itself. And in priority queue, we put the nodes we have yet to process. So we put the starting node, and then we start with the algorithm here. We pop the node we want to process, okay, and we put in distances the distance that it has from the source, okay. And then we travel its neighbors, and we increase the distance from 1, because if we are reaching W from VU, then if VU has distance, distance is VU, then that has distances VU plus 1 distance. Then if we have not seen it, or we haven't seen it, but this way is shorter, we update the info and we put it in the queue, okay? Like this. This algorithm has this running time, so it has n push queue operation and n extract minimum queue operations. So if in this case I use the heap queue library from Python that has these running times, but we can do a bit better. That was the key information. Here we can do a bit better if we use Fibonacci heaps, okay? But it's also in the order of the product of the number of edges for the number of nodes. So it's a very large number. And someone may want to use this, that is matrix operations. You can just define matrix on non-standard semi-rings, and they will give you the right answers as well if you are into very abstract linear algebra. And anyway, these are slower, but can be more easily parallelized and perhaps used. You can use GPUs and that kind of stuff. Maybe you can succeed. I suggest this way, which you will be seeing that it's very, very efficient, because we are just dealing with an approximation. So if the network just increases in size, you have 100 million nodes, either you have a huge server farm, or you have to be very smart in this stuff. So we know what is the median, okay? We have an array of sorted elements, and the median is the one in the middle, okay? We can generalize a bit and have, for example, the 1/3 median. That is not the element in the half of the array, but the element which stays at 1/3 of the elements of the array, okay? That's it. That's still an exact value. But we can also define this, the LQ delta median. Here, we do not take a single value, we take a set of value. Okay, a small set. If the data is decently distributed, then we can say that if you just don't get the median, okay, and we get a value that is close to the median, then it's fine. Okay? What is the idea? Is if you want to have the median of a distribution of values, you have first to compute all the values, and then to sort them. But sorting may not be your problem. If the computation is very expensive, as in the case of shortest path, single source shortest path algorithm, like the one we have seen in the slides before, then you have a big issue. On the other hand, we have the Huber method that says you can take a random sample of your whole sample, and it gives you the size of that sample, that is small s. And this method tells that with probability p equal to 1 minus epsilon, the median of the smaller sample is the LQ delta median of the larger sample. Okay? So, instead of taking all the nodes, you just take a very small subset, and you can decide the balance between precision here with delta and the probability you get the results right, and use that instead. So here I wrote the code, which is basically unreadable, I think. But anyway, this function here estimates the S value, okay? Here we take a random subset. Well, if the graph is already small, then it doesn't take a sample. But anyway. And here it just computes the values we are interested in for the nodes in the sample, and then makes the average. Make the averages for each node here, because we are doing the single source shortest path Dijkstra. So we make the average of all the distance of the nodes, and then we take the median of the averages array. So that works. To give you an idea, this is the value of S, the size of the sample. So you're not going to accept this kind of precision anyway. But if you try to be rather precise here, still the graph, the sample is in the order of 3,000 nodes. So you are just making computation of 3,000 nodes instead of some million of nodes. So it's a big win. And that is about performance, okay? In blue and cyan, we have the value of the mean, the exact mean of the shortest paths, okay? And the value we estimated with Huber method in the slide before. As you can see here, it's the number of hops. So you have to refer for the blue graphs to this axis, and for these ones to this axis, that is the running times. Okay? And so they are very precise and very close. And this is how the runtime is. So the green plot here is the exact method. Okay? So we are just doing Dijkstra for all the nodes. And as expected, it's basically a square line. Well, it's a square n multiplied by the log n. So it's a bit more than square. And you can see that with a very small network, that is 10,000 nodes, it blows up because that is 5 minutes. So if you think this kind of acceleration, okay, and you apply to networks of millions of nodes, then it's pretty clear you're not going to make it. Okay. On the other hand, this black line here is the one done with the Huber method, which is precise, we see, okay. And well, it's almost linear. In fact, it's, I believe it is n log n stuff. So this is going to work for large networks. But very large networks have issues. You're not going to use them on your laptop, okay? But still, with decent hardware, like, for example, 4 workstations, something like that, you may be able to do that kind of processing. And what about memory? That is the biggest issue. I mean, I love NetworkX. It has a lot of useful algorithms which really save your life when you want to do quick and dirty analysis. But the point is that default representation is this, okay? An adjacency list, which I'll be explaining in the next slide, okay? Other representation are these, the matrices, which we'll be seeing that is, are much more efficient, okay? Different representation have different trade-offs, space, time, depending on the algorithm you want to run, on how easy is metadata to manipulate if you have to do something that is not just raw computation on the shape of the network, but you have to use some attributes of the node, of the edges, something like you are analyzing a network of data coming from your websites, for example, okay? And so these representations are a bit harder to use with attributes, but are so much faster that you may want to consider them. I'll explain what I mean. So this is a simplified version of how things are stored in NetworkX. We have a dictionary of nodes that map each attribute with each node with its attributes. And here we have a dictionary, which is the adjacency list, true adjacency list, which maps each node with a dictionary that has as keys the neighbors of the node and as values a dictionary of attributes. So you can see that this kind of representation makes it very easy to work with attributes, because everything that can be a Python object can be an attribute. You can put it there, query rather efficiently, okay. It's nice. It's very close to a representation suggested by BDFL himself. But this is the problem. This is just 20,000, okay? So it's a very small network, okay? This in blue, it is the size of the image of a network represented as a NetworkX graph, okay? And we see that it grows linearly, roughly, but it's huge. That is a 32-bit machine, and we have 400 million bytes for a small network. And if it's a 64-bit machine, then it's going to be more like 900 million nodes. It means that if you study a network of 200 nodes, you are at 9 gigabytes. If you want just to reach 2 millions, well, you need 90 gigabytes of RAM, which is not going to be possible, okay? Here I put the dense representation, so we take just a NumPy matrix, and as expected it grows like the square of the size of the network. It's not good. But the sparse matrix representation is very efficient memory-wise, okay? Why? Because something that I did not point out in the slide where we had all the social networks is that complex network and social networks in particular are typically not dense. So you have n nodes and something like C n edges. And C typically is, well, for human social network it's the number, so 150, something like that. For like Facebook network, Twitter networks is higher than that, because people just tend to follow everybody. But still, it does not increase like the square of the size of the network, okay? So the matrix is basically sparse. There are very few nodes very few edges with respect to a dense graph, okay? And these are the disk-based solutions because, well, if you're not going to fit your network in RAM, you have to put it on disk. Of course, you can use stuff for scientific computation like HDF5, which you can manipulate in Python using the popular PyTables or H5Py packages. You can use MapReduce with tools like Hadoop or whatever you want to use, which does MapReduce. I love MapReduce. It's very, very interesting to use for many algorithms, but not every algorithm has a very nice expression as MapReduce algorithm, especially because many graph algorithms have been created before MapReduce. But since graphs are so important, well, there has been quite a research, so you're quite likely to find a decent implementation in terms of MapReduce. Then there are the GraphDB NoSQL databases like Riak, Neo4j, Allegro, which is the one from the guys making Lisp, Allegro Lisp, okay? And this is about, well, RDF and semantic stuff, usually. But anyway, this is very efficient, but it's Java, so, well, I do not know. No, I mean, the problem is the communication with Python is, well, it goes through JPipe, and I haven't yet benchmarked it thoroughly. I do not know how much really costs to convert things between Python and Java, okay? So maybe it just makes sense to use either Jython or Java directly, so if you want to use that. So I use a bit more this one because it's easier. Well, the bridge with Python is very nice, and of course, then you have to express the algorithms in JavaScript. You just push them in the server and have them running there because it's so much more efficient. Or you can just be using a regular SQL database. I've never done this, but it can work. Basically, if you pay attention, that I think it's going to work. Anyway, if you use a good database, I mean. Okay. And then we get to some more insights. We have talked a lot about how you can analyze graphs, but why you should be doing that. We are, well, into technology. We have to build systems that work. So, think about a typical social networking application, or your application, and you want to put their social data inside. Okay, you will be having something like that: a profile of users with name, email, connections. And probably you have a pointer to its posts, a pointer reference, something like that. Pointer, no, please. This is static, that is to say, the place where you put its activities, its posts, its comments, its tag is going to be static, okay? And this is not static. But anyway, think about this. When a user opens his page, which kind of data is read? Well, the post from his friends, for example, the tweets from his friends, from his followees, okay? That is just one person opening the page, his page. But when the million of people that open their homepage together access the data, what occurs? It occurs that high-degree nodes, high-degree people, very well-connected people, have their data accessed more often. Because basically the data access is, well, is related to the degree distribution, okay? So a user that has many high-degree friends has his profile read more often, okay? No, sorry, a user that has many friends, which means he has a high-degree person, has his profile read more often. So the degree distribution becomes basically the profile access distribution. And that could be used for caching, for whatever you want. You study the data, and you can predict what occurs. Or you can study the logs and see if it behaves like you would expect from this analysis. And if it does not, maybe you can ask you why. Okay? And what about the clustering coefficient? We know that networks have very high clustering coefficient. If you have a common friend, you are very likely to be friends yourself, okay? So, basically, we can think about clustering the networks and storing the clusters close. Well, this is something, I read a paper about this on internet computing last month. They have been doing a different backend for Neo4j that uses cluster detection to store the data on disk, so very low level. They claim to have had a performance increase. So that is an optimization at tool level. If you use the improved tool, you have that optimization in your application. Okay? So basically, they just do the communities, they compute the communities, and they store data of people in the same community very close. They are talking about disk level. I'm not sure if that can be applied to every kind of application. Still, maybe for sharding it is good. Okay? If you want to shard the data, you should probably take into account the clusters of the network. So you must know how to cluster the network. And perhaps you may want also to study the correlation between geography. Okay? If actually friends live together, they probably are going to access the very same server, okay? Or well, the same geographic location. That is, I think, it's reasonable, okay? So in general, the idea for social network analysis is that you can use that in every way to improve your existing code. So that is not just some mathematical toy you want to use. It may help you in real world stuff. And now about destruction. Okay. I enjoy network processes. You have a network. This is a different topic, okay? Social network analysis is a very wide thing. We have different stuff, of course. A network process, for example, could be a network destruction. So you have a network and you ask how you can kill nodes in order to break the network. That means if you, for example, are just designing some network, some electrical network, some networking network, well, routers, that kind of stuff, okay, you may ask, what have I to do in order to make my network more resilient? So, how are the errors going to occur? You choose the error model and you see how your network behaves. I will be seeing that, okay? Or you can ask how diseases or ideas spread, okay? We know, for example, the power law distributed networks are very good for diffusion. So it's both very good if you want to spread a virus or if you want to spread an idea. Because if you reach the high degree nodes, then they're going to spread wide, okay? And another very interesting is link prediction. If you want to build Facebook, you must know how to do this. You have to analyze the links you have in the networks and just predict which people your users would like to be connected with. This is another kind of network process. We will be seeing the first two. Well, if I want, this is very easy. Okay, it's an attack. You choose a centrality metric. You copy the graph because you're going to destroy it. Okay, anyway. Here you rank the nodes, and then you remove the nodes until you have disconnected the network. So we have a power law cluster network, that is a network I generated with an algorithm that generates networks with high with power law, degree distribution, high clustering coefficient, short average shorter path length, okay? And this is a random graph. So we start with a random attack. So we assume that we have every device in the network is equally likely to fail. We find that a power law cluster graph is very resilient because you have to remove 200 nodes That the original network had 1,000 nodes. Okay, so 1/5 of the elements in the network before breaking that. So it's very resilient to a random attack. On the other hand, if you know which devices to target, so if you want just to attack another country, okay, you want to break its power grid, and you know which building to attack, then you can just do a very small number of attacks, okay, and it's going to work. On the other hand, if they had a completely random electrical grid, power grid, then you could not, using ranking, break it. But this is just a lucky run. Just removing 10 nodes chosen at random, in this case, I broke the network, okay? This is likely to be a bit more, slightly greater, okay? And that is the last process, but really I put it there more for your information so that if you want to review the slide at home, you can just play with that. I will be putting some source on GitHub as well. That is the idea. You have 3 operating systems, okay, closing fixture, fruit, and Antarctic bird. And you have 3 viruses for each system, and you can choose the infection rate of each virus, how the system got immunized. For example, in this here, I choose that this is just immune. So when you run, it's like it has automatic antivirus, okay? And you can just run the process bit and see how the network is. The red ones are dead, and the green ones are immune, okay? And you can do that kind of stuff. For example, if you want to answer the question, what would happen if the fruit operating system would be as popular, half as popular as the other operating system, for example. Would the virus be an issue? You can run this kind of simulation and find out yourself. So I basically finished my presentation, and I want to thank you for your kind attention. Yes, I did.
Oh.
Well,
Sorry,
okay. She asked me if I used matplotlib to plot the graphs, and the answer is yes and no. I mean, NetworkX has a lot of backends to do visualization. Okay, one of them is actually matplotlib. So I didn't use matplotlib directly, but the library that was used by NetworkX was matplotlib. So in the example, you can see how to do them. I included the source, which was unfortunately not very readable right now. These were copy and paste from IPython notebooks, okay? So they were just embedded in the page, but you can also put them like usual in the usual matplotlib separate window, okay?
Have you analyzed any real live networks? Because you showed that some people analyze like Facebook, LinkedIn, Twitter networks, but were having problems, but you didn't mention whether you have analyzed any real networks.
Well, I got... he asked me if I did really analyze myself the networks here, and I started. Some of them also published their data, and most researchers did not, so I couldn't get the data, okay? Sometimes I found that my numbers do not match theirs, so I decided that it was a bit tricky, okay? And I'm not into the kind of stuff. I was mostly interested in getting some numbers to make an idea of how they are really made, because well, other people's data is, well, they have their formats. You have to put them. For example, I got a huge MySQL database drop, which was nearly unusable because I did not want to put up MySQL, that kind of stuff. But anyway, the problem I asked some student to do the crawl is it's very hard to make that stuff. You need a lot of time, and you may get very poor results. Usually, social networking platforms put restrictions, different kind. For example, LinkedIn, if you haven't got a profile, lets you watch just your ego-centered networks at like 2-3 hops away. With Twitter, you can download many posts, but you have a rate. You can't just download whatever happens, and so you have to choose. So that is a very interesting kind of experiment, but I'm not really into it. There is a paper from one of the guys there that claims to have found a way to sample Facebook that can be applied to other social networks in an unbiased way. So he says that although he samples the network, he does not introduce the bias. So the conclusions he can draw are likely to be correct. I would start from that if I were you. Okay? If you send me an email, I can just. Okay.
With the network X, for visualize a very, very large network is less efficient, takes more time. Instead, exporting JXF is very fast. There is a way to optimize this process, a way to...
Well, I believe that he asked me whether there was a way to visualize very large networks, I think either with NetworkX or to export them in JX and then visualize them with another tool which is more efficient. Which tool do you use? Which tool do you use?
I use a software of myself to take Twitter follows and
Okay.
visualize the connection between different users.
Okay. No, I was asking him if which kind of visualization software he used, but I think that he did that himself. So I tried to answer his first question. So you can easily use NetworkX to export network to a very wide array of formats. Among them, I think there is JEXT. You can just check it out. There are a bit of a list. If I would really want to visualize a network, I would build, perhaps even with NetworkX or perhaps with GraphWidth plus NetworkX, a multipass algorithm. So the problem is that most algorithms have a running time that depends on the size of the network more than linearly. Perhaps it's square, perhaps it's n log n, something like that. But if you try to break the network into components, and then you apply the algorithm to the components, and then you place the components using the algorithm as if the components were graphs, then you're probably going to have a beautiful result. But really, visualization, well, I work better with numbers. I'm not very visual kind of guy. Besides, if you really have 100 networks, it's going to be 100 million nodes. It's going to be pretty messy anyway. But it's more art than getting info from such a large network. I mean, well, you have surely seen that the internet graph, the one painted with the back painted in black and the edges color. It's very beautiful, but you really don't get what occurs, I think. At least I don't.
the social networks.
Yep.
You briefly mentioned that you could look at the connectedness of someone and use that to compare that in the, like Apache logs or something to see if they were being accessed more often. Do any of the talks that you cited actually do that?
No. No, that was just an idea. I mean, okay. He asked me to explain whether I know of someone that compared access logs to the study of the network. Okay, so I study the network of my application, and I see if the access pattern predicted by the social network analysis match with the analysis done on the logs. I would do that if I had an application. The problem is that people from startups and business companies usually do not publish their internal research. On the other hand, people from the academia tend to publish their research, but they do not have data, and if they get it, it's from companies that do not want them to share them. Because, you know, there have been some attacks that from an anonymized network, they just reconstructed the real social network. So it's a bit tricky to give that data away. Since I haven't got a company, I don't have that data, and so I did not analyze that myself. But I think that if you have, you may find some insights from, we get some insight from that, okay?
Okay, so thanks Enrico, and we finished it a little earlier, so now there should be the coffee break.
Okay. Thanks.
Ha un worst case o è sempre così ottimale l'approssimazione? O nel worst case può sballare qualcosa?
Allora, il problema...
È pazzesco l'approssimazione, no?